PCA can hide structure. UMAP makes your embeddings tell the truth in 2D. By the end of this video, you will understand when UMAP gives clearer, more faithful two-dimensional views of your high-dimensional data, and how to try it on a small example in Python. I'm Professor Pi, teaching AI foundations with simple Python. UMAP is what people reach for when tsni or PCA miss patterns you suspect are there. It is not a classifier. It is a way to make a map that places similar items near each other, so you can visually inspect clusters and relationships. In practice, it helps at the exploration stage when you have embeddings from a model and you want to see if the structure matches labels or intuition. At a high level, UMAP builds a fuzzy graph of local relationships in the original space, and then finds a low-dimensional layout that preserves those relationships. Think of it as learning the neighborhood structure first, and then drawing a map that keeps neighbors together. It tends to preserve both small clusters and larger continuity better than plain PCA. Though choices like how many neighbors to consider change the result. We will build a tiny reproducible toy dataset, embedded into 2 dimensions with UMAP, test projecting new points into the same map, inspect nearest neighbors on the map, tweak the neighbor's parameter to see the effect, and add a quick color plot to relate points back to simple labels. This snippet builds a tiny, reproducible dataset and maps it to 2 dimensions using umap-learn's UMAP. The variable RNG creates a deterministic random number generator, so results are stable. The array X holds 120 5-dimensional points. The first half is shifted by 2 to form a visibly separate group. The call to UMAP with 2 components and a fixed random state produces a consistent 2D layout. The method FitTransform takes the high-dimensional X and returns Y, a 2-column array that places similar items near each other. The printed shape confirms a full 120-point 2D embedding, signaling that the reduction step completed correctly. Now, we will show how to get coordinates for new items without retraining the whole map. This example shows how umap-learn's UMAP can embed unseen samples onto an existing layout. The variable is a reusable model that learns the structure by calling fit on X. The variable new holds 2 slightly perturbed vectors derived from earlier data, simulating fresh items that are similar to known points. The method transform projects these new vectors into the same 2D coordinate system without refitting the model. The array Z returns their coordinates, allowing direct comparison with Y. If new points are truly similar to their sources, they appear nearby. The printed coordinate Z0 shows where the first new point lands on the map. Next, we will check who sits near a chosen point on the map. This code inspects the 2D UMAP layout by measuring local neighborhoods. The vector D stores Euclidean distances from the first embedded point in Y to every other point, capturing how close items lie on the map. The function argsort returns a ranking of indices by increasing distance. Skipping index 0 drops the point itself. The array IDX holds the top nearby candidates, and vals stores their distances so you can gauge tightness. Smaller values mean tighter clusters and better local preservation. The printed indices and smallest distance show which items are closest in the embedding, offering a quick check for cluster compactness. Next, we will change how many neighbors UMAP considers when it learns local structure. This snippet demonstrates how umap-learn's nNeighbors parameter changes the 2D layout. The model UM5 uses 5 neighbors, emphasizing finer local structure compared with the default setting. The array Y5 is the new embedding from FitTransform on the same X, so differences arise solely from the parameter. The variables S1 and S2 compute overall spread via the standard deviation of coordinates. And R reports the ratio between new and original spreads. Decreasing n neighbors usually sharpens small clusters, sometimes reducing global spread. Increasing it smooths clusters, but strengthens large-scale continuity. The printed ratio summarizes how the layout's dispersion shifted after the tweak. Next, we will add a simple plot to tie visual clusters back to labels. This example adds a simple visualization by coloring points with Matplotlib. The variable y assigns labels by thresholding each row's mean in x, creating two groups that roughly mirror the offset we introduced earlier. The function plt.scatter plots the UMAP coordinates in y, using the label vector y as the color argument, and viridis for a perceptually uniform palette. The calls to title and tight layout improve readability for quick inspection. If labels align with visible groupings, the embedding likely preserves meaningful structure. The printed unique label count confirms how many groups were colored, helping you relate clusters to known categories. If you move this toy into a real project, treat the labeled colors as a sanity check for embeddings from your model. You can embed tens of thousands of vectors, but expect computation time to grow, and consider approximate neighbors or batching for speed. Recap: UMAP is a dimensionality reduction tool that makes local and global structure more visible than PCA in many cases. Use it when you want faithful, interpretable two-dimensional maps of embeddings for exploration or labeling checks. One caveat is that parameter choices like the number of neighbors change what the map emphasizes. Next step: tune n neighbors and observe how cluster tightness and global continuity trade off. Or try changing the distance metric to match your embedding type. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.